Today we'll be calculating the rate of change for an exponential function. Finding the rate of change of exponential functions is very similar to that of linear functions. You still use the slope formula to calculate the rate of change, but you were told by the interval which 2 points to use for your slope formula. So a linear function, you choose any 2 points on the line, and the rate of change between them will be constant. For an exponential function, I have to tell you which 2 points to use because the rate of change is different at different points. So let's take a look at this table in example 1. The table at the right represents a type of bacteria that doubles every 36 hours. A petri dish starts with 12 of these bacteria. Calculate and interpret the average rate of change from day 2 to day 5. So these are the 2 points that we're going to use in order to calculate our rate of change. So we've got 230 and 121. So we'll calculate the slope between them. So y minus y over x minus x, which will give us 91 over 3, which will be approximately 30.3. So what that means is between days 2 to 5, bacteria grew at a rate of 30 per day. Okay, so I told you which 2 points to use, and then you calculated the slope or the rate of change between those 2 points. All right, let's look at the second example. Second example is a little bit different in that we don't have a table of values, and we'll have to find the points which we're going to use for the rate of change from the graph itself. So Jasper has invested an amount of money into a savings account. The graph to the right shows the value of his investment over a period of time. What is the rate of change between years 1 and 3? So the first year, if we look at the graph, here's 1 for our year. And if we look at where that lands, it's before the 600. So this interval here is between 4 and 6. So I would say halfway is about 500. I would say this is approximately 550. And if we look at year 3 and find out where that investment amount would be, it's about halfway between 1,000 and 1,200. So we'll call this 1,100. So the points that we're going to use for this rate of change will be 1, 550, and 3, 1,100. Okay, so I'm going to tell you to pause the video here and calculate this slope, and then press play again once you have the slope. Okay, so let's look at what the slope is between these 2 points, or this interval between years 1 and 3. So 1,100 minus 550 over 3 minus 1 is going to be 550 over 2, which is 275. So what does this mean? This means a growth of $275 per year. Right, we're going to use the same table for example number 3, only we're going to have a different interval this time. Jasper is curious about how the rate of change differs between years 3 and 6. Calculate the rate of change using the same graph. So now we need to look at year 6. So year 6 is up here. So I'm going to call that approximately 3,100. So here, year 3, which we used in example 2, and then now we're looking at year 6. So go ahead and pause the video and then come back and hit play again once you've found this rate of change. All right, so here we go. 3,100 minus 1,100 all over 6 minus 3. So 2,000 over 3 equals 667.67 when you round that. So what this means is that between years 3 and 6, there was a growth of $666.67 per year. So between these two examples, example 2 and example 3, it demonstrates how the rate of change is different depending on the interval that you're looking at for an exponential graph. So when we looked between years 1 and 3, we had a growth of $275 per year. And when we looked through years 3 and 6, we had a growth of $666.67 per year. Okay, so the interval that you look at will have a different rate of change each time on an exponential function. Okay, so let's do a little bit of graph analysis here on example number 4. Looking at this graph, the first thing that we're asked to do is to determine whether or not it is a growth or a decay. When you're looking at the graph, it's increasing from left to right, so that tells us that it's growth. The x-intercept means where's the graph crossing the x-axis. This is not crossing the x-axis at all because the x-axis here is an asymptote. So this would be none. What is the y-intercept? So where are we crossing the y-axis? You can see it right there. And that's 0, 3. So you're writing that as a point because your y-intercept is a point on your graph. Is this a function? So this goes back to what we talked about during first semester and this vertical line test. So exponential growth graph will pass a vertical line test. So here we're going to say yes. And then our domain and our range. Our domain, we can substitute in any value of x here. So our graph tells us that our domain is going to be all real numbers. Last week I talked to you a little bit about interval notation. So this is interval notation, negative infinity to infinity for this graph. This is set notation, x such that x is an element of all real numbers. Our range, a graph only exists above the x-axis or where all of your y's are greater than 0. So for our range, it's y such that y is greater than or equal to, actually, let me erase that or equal to. It's just where it's greater than 0. Okay, so our range is 0 to infinity in interval notation. I'm going to have to pause the video now in order to erase that. Okay, I was able to erase. Where is f of 0 on my graph? So f of 0 means my x is 0. That's at 3. So that was our y-intercept. F of 1 is right there at 6. And that's going to lead me to my next question, which is the average rate of change from this interval of 0 to 1. So we're going to use 0, 3 and 1, 6 and calculate the rate of change between those. So it's 6 minus 3 over 1 minus 0, meaning the rate of change between these 2 points or over this interval on your graph is a 3. Okay, so I'd like you to pause the video now and go ahead and complete example 5. Look at the graph that's given and answer each of these questions. And don't resume the video until you've tried each one of these questions. All right, so finishing up this last example. When you look at this graph, the graph is falling from left to right, which tells me that it is decay. Your x-intercept, you do not cross the x-axis because it's an asymptote, so here we say none. Your y-intercept, 0, 2. Is this a function? It passes a vertical line test anywhere that I check. So yes. Our domain, similar to example 4, is going to be all real numbers in set notation. And in interval notation, that's negative infinity to infinity. You do not need to give me both of these answers. Whichever notation you like better, you can go ahead and use that. Range, similar to example 4, is going to be all of the y values that are greater than 0. So y such that y is greater than 0. In interval notation, 0 to infinity. F of negative 1, we look at our graph, negative 1 leads us to a y value of 8. And f of 0, we've already used that one. That was our y-intercept, 0, 2. So you're calculating the rate of change from this interval, negative 1, 8 to 0, 2. So your slope, 2 minus 8, 0 minus a negative 1 is going to be a plus 1. So we have negative 6 over 1, making our rate of change negative 6. Okay, so that concludes our notes for today. Go ahead and start your homework, which I will check tomorrow.